Alright, in this video, we'll be doing a crash course on integration by parts. This isn't to try to slowly teach you, this is a crash course. Hopefully this is just to refresh your memory or to review and to just remember the techniques to solve these types of problems, okay? So let's quickly review what integration by parts is. We have integral of u dv is uv minus v du. You have a product of two functions. This comes from the product rule, okay? So if we d by dx, let's say, or let's say it as uv, take derivative, so uv prime is, the product rule is u prime v plus v prime u, okay? So we integrate both sides, we get uv is integral of u prime v plus integral of v prime u. You could write the u prime as du and the v prime as dv, and then you reorganize to get this, okay? So this is where integration by parts comes from. When you have a product of two functions, that's the good candidate to use integration by parts. So if you remember, we have kind of three types of problems for integration by parts. Let's do example one, okay? We have the, okay, I'm gonna write very big, so hopefully it's clear on the video. We have the integral of x ln of x dx, okay? So how do we solve this? We have to choose a u and we have to choose a dv. How do we choose which one, or how do we choose each? We have an x, we have an ln x. Which one goes where? Okay? The trick here is, if you put dv as ln x, what would v be? So that's the integral of ln x. Do you remember that off the top of your head? If you do, great. It might not help you to solve this problem, but if you do, that's good. The integral of ln x, we actually need integration by parts to solve it. So we'll do that in the next example. Let's call this actually example 1a. So we had to choose u as ln x, because we know the derivative of ln x. We don't know the antiderivative of ln x. Du would be 1 over x dx, that's easy. So dv is what's remaining, x dx. So v would be half x squared. Remember, we don't have to have a plus c, since this plus c would cancel out in your calculations, okay? With that, and then you'll have another plus c at the end anyway. Okay, so let me use a different color. Remember, integration by parts is uv minus v du. udv is uv minus v du, okay? So we do integration by parts. uv would be half x squared ln of x, that's uv, minus integral v du. That'll be, we have a half in the front. We have a x squared times 1 over x, that'll just be x dx. Okay, let me check my work that was correct. Looks right. Okay, so this we know how to integrate. That's simple power rule. So we get minus a fourth x squared plus c, and that's how we solve this one. Okay. Let's do example 1b. I said let's do integral of ln x dx. So here, again, we have to choose our ln x as u. What about dv? That's the confusing part for first timers of integration by parts. What's remaining? We have a dx remaining, or 1 dx, okay? So that could be your dv. So du would be 1 over x dx. V would just be x, okay? So again, uv minus v du will be x ln of x minus integral of x times 1 over x is just 1, so we're left with dx. So we integrate this, that's very easy. X ln of x minus x plus c. Okay? That's the first category of integration by parts. The trick was we had to pick u as something we know the derivative of. dv has to be something we know the antiderivative of. Okay? Okay, we're on example 2 now. We have integral of x sine of x dx. Okay? So how do we choose our u? How do we choose our dv? Okay? In this case, we choose our u to be x. Okay? And then dv would be sine x dx. Okay? du, that's easy. That's just dx, or 1 dx. V would be minus cosine x. Okay? What happens if we flipped it? If we chose dv to be x, and then v would be half x squared. So then remember, integral, in this portion of the integral, you have a x squared. Okay, and then your du would have been cosine. So x squared times cosine, it looks like you're getting even worse. We had x sine x, now it became a x squared cosine x, so it looks like we're going the opposite way. So we want to reduce the power of this x. Okay, so that's why we choose u as x, du becomes dx, we reduce the power. Okay, so again, uv minus v du, we get minus x cosine x, plus, because it'll be minus negative, okay? So cosine x dx, because cosine times dx, 1 dx, so you just get cosine x dx, okay? So see that this is a better integral than this one. This one, we know how to solve. Again, in the other, if we had flipped the u and dv, we get x squared cosine x, something like that. There'll be a half out here, something like that. So we're going in the wrong way. Okay, this is easy to solve. Okay, integral of cosine is just sine. Okay, so that's how we solve that. Okay, so if we had, let me do example 2b, like 2 powers of x, so x squared sine of x dx. This one we have to use integration by parts twice, so let's do it. U would be, we choose x squared, remember the technique, we want to reduce the power of x. Du would be 2x dx. dv is what's remaining, sine of x dx. V would be minus cosine x. Okay, so this integral is equal to uv minus v du minus x squared cosine x plus integral of 2 times x cosine x dx. This plus because it'll be minus and negative, so it becomes positive, and then 2x cosine x still there, okay? So this one, again, we do integration by parts. U would be x, du would be dx, dv would be, what's remaining? Cosine x, dx, v would be sine of x, okay? So we get minus x squared cosine x plus 2 times uv minus v du again will be sine x sine of x minus integral of sine of x dx. Okay? This we know how to solve. This is the same. Let's distribute this 2 plus 2x sine of x. Integral of sine would be minus cosine. There's a negative there, so it'll become a positive cosine. And then I distribute the 2 in, plus c, okay? That's how we solve this one. So if you have x to third power, x cubed sine x, you need to do integration parts 3 times. So you can see that if this power of x gets bigger and bigger, you have to do integration by parts that more times, okay? So there's a quicker way to do this. We call it the tabular method. Okay? So how I like to show it is, we have a column for u, we have a column for dv, okay? We pick u and dv to be the same way as we did up here, so we want to reduce the power of x. So we'll have u as x squared, dv was sine x. I'll omit the dx over here, okay? So we keep differentiating u until we get to 0. So derivative of x squared is 2x. Derivative of 2x is just 2. Derivative of 2 is just 0. So we stop there. Okay? We take the antiderivative, or we integrate sine x the same number of times. So we get minus cosine x. Minus sine x, we keep integrating. And then integral of minus sine x is just cosine x. Okay, there's that. And then we go diagonally, so draw lines, diagonal. Okay, and then we always start with positive, and then we alternate. Okay, so positive, negative, positive, okay? We multiply all the terms together. This plus is a plus 1, this minus is a minus 1. So x squared times 1 times minus cosine x, that'll be minus x squared cosine x, minus 1 times 2x times minus sine x. Those negatives would become a positive, so it'll be plus 2x sine of x. This one will be 2 times 1, positive 1 times cosine, so plus 2 cosine x plus c, and we see that we get the same answer we got up there. Okay, so this is a quicker method to solve these types of integration by parts problems. Okay. And then finally, we'll do an example where, I don't know how to describe it, but once you see it once, you know how to do it, okay? So let's do example 3. We have the integral of e to the x sine of x dx, okay? So we have to choose a u, we have to choose a dv. Does it matter in this case? It doesn't, but I personally am more comfortable, especially when there's a sine 2x or something on the inside. I like to differentiate the sine or cosine because it's just multiplying instead of dividing. I'm just more comfortable with multiplying. So I choose u to be sine x, but you could choose u to be e to x, doesn't matter in this example. dv is e to x dx. du would be cosine x dx. v would just be e to the x, okay? So this integral is equal to uv minus v du, e to x sine of x minus integral of e to the x cosine x dx. Doesn't seem like we got it anywhere. So let's do integration by parts one more time. U would be cosine x, du would be minus sine x dx. dv is e to x dx still, v is just e to x still, okay? So we get e to the x sine of x minus parentheses uv minus v du, once again e to x cosine x, okay? And then plus integral of e to x sine of x dx, okay? So we got back the original integral. Was that what we wanted? Seems like we're getting nowhere, but this is the technique. Remember, we call this I. So this I is equal to this, I is equal to this, okay? This is also I, so we can rewrite it as I is equal to e to x sine of x minus e to x cosine x minus I. Okay, we distribute the minus sign, and then this is the I, so it becomes minus I. We can solve for I now. So we add it to this side, it'll be 2I is equal to this guy, so I is equal to e to x sine x minus e to x cosine x over 2, okay? So that's how we solve this type of integral. Okay, so there's basically 3 categories that I showed you. One was you had to pick u, so let me just get the paper back. We picked u as something we know the derivative of, and dv as something we know the antiderivative of. The second type is when you have x with like sine or cosine or e or some exponential, something like that. Something with like a kind of repeating derivative type of thing. We wanted to reduce the power of x, so we set u to be that power of x, and then dv would be that sine, cosine, or exponential, something like that. We can use the tabular method when it's useful, and then this is the third type when you have product of 2 functions whose derivative is like kind of repeating type of sense, like e and sine, e and cosine, but there's the special one, secant cubed, you also use this method. Okay, so this is basically in how I like to think of it, these 3 types of problems, okay? So hopefully this video helps you to just recall how to solve these types of problems, or maybe you didn't quite get it before and now you do, so that'll be good for you. I don't know what else to say. If this video helps you in any way, please hit that like button, and please subscribe to the channel if you want to see more crash course videos like this.